So thank you to John, Stamm, and Parker Norton, who will be presenting today. They're from the U.S. Geological Survey South Dakota Water Science Center, and their presentation is titled Regional Climate Model for the Missouri River Watershed, 1981 to 2050. And after the presentation, we will have time for some questions and discussion. So thank you.
Okay, can you hear me? Can you folks hear me out there?
Yes, yes, we can.
Okay,
yes, we can.
Great. Just want to check that. All right. Yeah, I'm John Stamm, and I am with a PhD student from South Dakota School of Mines.
I'm Parker Norton.
And Parker and I have been working together for a while. A lot of what we'll be presenting here is actually Parker's PhD dissertation work. So I'll give you an idea of kind of the work that he's doing. Just go through an outline. I mentioned the Missouri River in the title of this presentation, and the reason we're focusing in on that is because of some Streamflow trends work that was done early on, and I just want to just kind of introduce you to that, give you a little history of how we started working on this climate and Streamflow trends in this area. I'll just kind of go over some of the projects we've been associated with here at the South Dakota Water Science Center in Rapid City. I'll talk about some of the data sets that we've been using, some of the statistical downscaling models we work with, and then a model that we've been doing an awful lot with, a dynamical model called the Weather Research and Forecasting Model, which people call WRF, W-R-F, WRF. So you hear us say WRF a fair bit. Again, we're focusing in on the Missouri River watershed. We have a couple of simulations. We'll talk about a validation period, 1981 to 2000, and then projections out to 2050. And then I'll just kind of give some concluding remarks where I'll talk about some publications and model output. Okay, so starting with the streamflow trends in the Missouri River watershed. This kind of goes back before us with the USGS. I ended up joining the USGS in 2008 or so, and prior to that, Parker and Mark were working on looking at streamflow in the Missouri River watershed. They were looking at annual and seasonal streamflow trends. They kind of had various time periods, but most recent work we've been doing is going back to 1960. We've got a publication coming out where we look at streamflow trends from 60 to 2011. I got involved with things, again, after part of the streamflow analysis a little bit later, so the three of us got a pub that's coming out pretty soon here. I'll talk about that later. Kind of looked at 227 streamflow gauges that had complete records from 1960 to 2011. And looked at trends in those gauges and really used the non-parametric Kendall-Tau test to evaluate statistical significance of trends. And I'll show you a little bit. So here's the Missouri River watershed. It's colored by these 6 kind of sub-basins, 1 through 6, 1 kind of the upper stream most in the Missouri River, and progressively going downstream to 6. We'll come back to this figure and talk about these areas. But what this plot also shows is these triangles. You can see these red triangles that point downward, and then blue triangles that point upward. And those are locations of gauges that had significant trends, either upward or downward, in annual streamflow over that time period, 1960 to 2011. This is part of a pub, a figure from a pub that's coming out. You can kind of see 3 populations here, and here's one of downward trends. I'll just mention real briefly that that's a result of groundwater pumping and irrigation activities down in this area. There's a paper by Wen and Chen in Journal of Hydrology that talks about that nicely. Then you see a couple of other populations in the region. And you see this one of downward trends here, kind of the upper Missouri River area. And then this area right here, and this upward trends, and some of these upward trends are really significant. This is an area that's largely is glaciated. And so what I'd like to do is kind of show you one gauge right here, give you a little bit of an idea of the trends. Again, this is glaciated terrain. This is the James River. James River watershed, the gauge at Scotland, South Dakota. The X's here are the individual water year. Water year begins October 1st, by the way, and goes from 12 months from there. The X's are the individual water years, where we've got, you can see those for each year. And then this line right here, this black line, is a 10-year moving average. And you can see streamflow trends really kind of ramped up, and a matter of fact, at some of these individual water years, you got an order of magnitude increase in streamflow trends, annual streamflow trends. You can see this green line here is precipitation for the watershed based on a data set called PRISM, which I'll introduce a little bit later. It's really kind of going up as well, but boy, the streamflow is really kind of ramping up. If you look at this area, here's the James River, and this is kind of the edge of the watershed, and you can see that there's a lot of lakes in this area. One lake here, Wabae Lake, you can see it's relatively bigger. So this is eastern South Dakota. But you know, if you look at this area, there wasn't always lakes. These lakes were largely dried out. You know, this is glacial terrain, a lot of depression, poorly drained, that kind of thing, typical for glacial areas. And if you go back, and here's our plot again, and if you go back, I showed actually this elevation of Wabae Lake. It was dry, and then it started to wet up, and then it really started to wet up. So some of these streamflow trends we actually think is because the shallow groundwater system really started to saturate up, and then when it rained, the water had nowhere to go. So the streamflows really responded fast. So the point I want to bring in here is that we're kind of looking at these streamflow trends and thinking about climate, but other things like interaction with groundwater may come into play in this. Okay, so let me show you some. So that kind of sets the scene as to you know, these trends and interested in climate and so on. There was a few other projects. Again, before I was with the USGS, Mark started working, got the attention with these streamflow trends, got the attention of Susan Scoggin down in Fort Collins, and they started to join forces. They got a little bit of money from the USGS Central Region Integrated Science Partnership, and then a little bit from the National Climate Change and Wildlife Science Center. And they're kind of getting into this realm of climate analysis, and then they hired me on in particular to help with the climate stuff, so that's when I came on. We got a little bit of money from the PPP LCC early on to help get things started. And we're really kind of interested in what's going on here in this Prairie Pothole region, which is this kind of stippled area here extending outside of the Missouri River Basin as well. And I'll talk a little bit about that a little bit later on. Right now, I'm still kind of engaged a little bit with Susan. We got some money from the North Central Climate Science Center to kind of keep me engaged to some extent, and also the Great Plains LCC. A lot of money that we got came from actually the South Central Climate Science Center and National Park Service. They were interested in the response of karst aquifers in the Black Hills here. You can kind of see in this area of western South Dakota, we've got the Black Hills. And I've got a lot of karst terrain up in here. And what would be maybe the response of karst aquifers and species vulnerability that maybe depend on those aquifers and flows and spring flows and so on. So we looked at the kind of what's going on in the Black Hills, and also down in Texas, we've been working with the Texas Water Science Center, looking at the Balcones escarpment, where there's also karst aquifers and species down there that may be vulnerable to change. So that's another thing. National Park Service, mostly that's in the Black Hills. I'll just show you one little plot here. This is a little elevation plot from a high-resolution climate run that we did. They have a bunch of location of climate stations, and they were interested in what might be the projections of climate at those climate stations. So we did a high-resolution climate model for that. And it would be tied in, a publication that will be tied into their weather station inventory. All right, So anyways, that gives you a little bit of a background on the funding and how we kind of got here and why we're focusing in on the Missouri River area. We've done a fair bit of work with some statistical models. I'll just kind of go over those quickly. A lot of you probably have used these. The PRISM model, Parameter Elevation Regression on Independent Slopes model. It basically provides monthly precipitation and monthly min and max temperature. And then it also covers the lower 48 states, the conterminous United States, at a 2.5 arc-minute spacing, which is about 4 kilometers. And it basically interpolates between weather stations, and it goes back to 1895. This just shows a map showing this PRISM data set, just so you get a little bit of a feel of the resolution of how it might look like. This is the 20th century average of mean annual precip. We use this as a baseline, and we've got similar thing for temperature, min and max temperature as well. But just give you an idea of this data set. This is a plot we'll come back to, and this is for the Missouri River watershed, and this just shows if you were to take, maybe let me back up one here, if we average up all of those points in the Missouri River watershed and do that for each year, now we would get this plot. And so this is showing top the kind of temperature trends for the Missouri River for each water year. We got about a 0.8 degree C increase per century, and then a 36 millimeter increase per century in precipitation. So we'll come back to this plot a little bit later. Parker's also been working with a statistical downscale model called DAMET, which comes out of Oak Ridge. It had a daily time step, provides precip and min and max temperature, and some other variables are there as well. One of the nice things about this is that in addition to being for the United States, it extends into Mexico and southern Canada. It's got a 1 kilometer grid spacing. It only goes back to 1980 though. And so he'll discuss that a little bit later on. This is just a map just to show you the extent. Recently, I've been getting more and more involved with some of the work in the Great Lakes. Some of my more recent work is kind of in this area. And so DAMET is nice there because it extends into Canada, so we can show those Canadian basins up there and so on. All right, so that's just some of that. I'll give you a little bit of background on this weather research and forecasting model that we've been using as well. It's also called, so it's called WRF, and the version we use is the Advanced Research WRF model. It's a dynamical regional climate model developed by NCAR and maintained by UCAR, and they develop it as well. One of the reasons I got tied on to this is a lot of these projects wanted more than temperature and precipitation. They wanted a lot of other hydrologic variables. They wanted daily time steps, which is hard to get from statistical downscaling, and also stuff in the atmosphere. We're looking, one of the projects with Susan was looking at migratory birds. We were kind of interested in temperatures aloft and all that kind of stuff. So dynamical regional climate models provide those kind of estimates, those kind of simulations. And it turns out Gary Clow, he's in Boulder, and he's with the USGS Earth Surface Dynamics program. He's actually was using this model WRF, so we already had it set up. And so I said, well, if USGS has kind of got it going, let's kind of hook up with Gary. And then Steve Hotstad was doing a bunch of simulations as well, and I didn't want to duplicate what he was doing, but he was not using WRF. So this kind of filled in the gap and complemented what he was doing. And we're talking about 2010, 2011 or so when we were doing this work, and all of those models were just being run at that time. Gary had access to the University of Colorado. His office was actually there, and NSF-funded Community Surface Dynamics Modeling System. And he actually, in the USGS, through him, had purchased a bunch of processors, 16 8-core processors, which gave 128 nodes that we could use just for WRF simulations. And when you do that, just to give you a little idea, when we do a 50-year simulations, we got those processors running pretty much continuously for 2 months on the short end, 5 months, depending on the resolution and the extent of the model. So it does take a lot of time to do one of these longer simulations. 50-year simulation we typically did was like 2000 to 2050. Our simulations, we got a couple. We got actually a 12-kilometer simulation for a small area. I'll show you that. A couple of 36-kilometer grid spacing simulations. It's got 36 vertical levels in the atmosphere. It's got a soil model for infiltration, 4 levels there. It computes at a relatively short time step, but then integrates that and kicks that output every 3 hours. Okay, so just to give you an idea of the areas that we've been modeling with this WRF. Here is the representation of North America from a general circulation model, a global climate model. This is CCSM3, and it shows the terrain. And you can see that it shows the Rockies and the Sierras relatively coarsely, just basically kind of a hump right there. You certainly don't see details like the Black Hills and the, Balcones escarpment. Here is our larger model domain run, the 36-kilometer domain run. You can really kind of see a lot more detail, and you have a lot more confidence that you're going to show regional variability within the climate model when you show these terrain features. So that's our large model extent. We also did this 12-kilometer run, and so when we did that, just to have it run in a reasonable amount of time, we had to pull in the edges a bit. And so we got a 36-kilometer run showing this full area, and then in this red triangle, a red rectangle, we've got a 12-kilometer run. One thing that I'll mention is that we're going to really show the larger area in the rest of our analysis here. We've got a little bit of bias on precip. When we pulled into the smaller domain, got a little bit more control of the boundary conditions of this model, kind of controlling things a little bit more, and the precip kind of settled down a bit. So we actually get this run actually has a better precip than the stuff we're going to show you. I'm going to zoom in on this 12-kilometer area. This is what it looks like at a 36-kilometer resolution. There's kind of the Black Hills right there. And then if we go to 12 kilometers, you're really starting to see some of these details, and which is kind of the stuff where the Park Service in this area kind of wanted to show this detail and this variability in here. Okay, Advanced Research WRF, so that's the area in the domain. It's got a whole suite of variables, surface and aloft, as I mentioned, winds, air temperature, moisture. At the surface, of course, we got precipitation where it breaks it into frontal and convective, snowfall, snowpack, ET, infiltration, soil moisture down in the soil, and also soil temperatures, and a bunch of other variables that we get out of that runoff. All right, so when we run these models, this is not like a GCM. It has boundaries, and it has to know what's coming in and what's coming out. And we get those from, the WRF runs get that from GCMs. One GCM we've been using is a reanalysis. It really is, it's a GCM that's forced to fit observations as much as possible. This is the kind of stuff that the weather forecasters use these data sets to get their models kind of up and running and started before they do their short-term forecast. We got data from 1981 to 2010 from the Climate Forecast System Reanalysis, PARC, or we'll refer to this as CFSR. And there's, you can see it's a half-degree resolution, a lot of vertical levels, and it also goes for soil levels and so on. Just a little more detail there. We also, so this is simulating, kind of trying to simulate pretty exactly the climate observations. When you do simulations out into the future, you also do what's called contemporary. It's not really giving you the exact details of historic changes, but it's showing the behavior of climate during historic times. So it's not exact, so they call it contemporary instead of historic. We got 2 runs, 1981 to 2010, and then 2000 out projecting to 2050. The one run that we selected was the Community Climate System Model to provide boundary conditions for this. And again, there's the resolution, and that has a 10 soil level model. So anyways, there's some of those details. Okay, so this is this plot from PRISM that I showed you previously, where we showed those trends and so on. So precipitation at the bottom, going back from 1900 out to 2013 here. Here's temperature at the top. I'm just going to turn that to black so that it can pop out a little bit more. And here's this reanalysis from CFSR. And you can see when we run WRF that, well, let's see, there's my mouse. Okay, that we actually match temperature pretty good. It looks like we're dipping down a little bit cold here in terms of basically running WRF with observational data at the boundaries. All right, that's kind of what that CFSR is. We got a little bit of a cold bias here. Again, as we pulled in domain, that's the kind of thing that might make that disappear if we don't do such a large area. But overall, we're seeing similar kind of trends at least, but we got a little bit of a bias there in the reanalysis. We did kind of check other kind of physics package for precip, and they all kind of did the same thing. All right, so I just got rid of those lines, and I just wanted to show you the CCSM raw data. Again, this is for the period 1901 out to 2000. It's simulating the behavior of climate, not the actual up and downs, right? But you can see there's a pretty good match there in precip and in terms of temperature as well for the Missouri River watershed. This is, again, the average for each water year for the Missouri River of annual temperature and annual precip, and then kind of marching out into the future. Here's our WRF runs, and I'll just kind of pull off the next slide. I'll just get rid of the CCSM stuff. And so here's we got a little bit of a cool bias in terms of our WRF run. We do have this wet bias, again, which we got rid of a lot by pulling in the boundaries a bit. It does work better in the plains. So if you get rid of the higher elevations, actually a lot of this precip bias goes away and we get a much better match. And that was kind of important for us because we were doing a fair bit of work on the prairie potholes area. That was kind of our focus area. And also the Black Hills and the plains surrounding that. Okay, so this shows just kind of how are we doing on an annual cycle. The black line here is the prism stuff, which is kind of what we're trying to match. The thicker red line is WRF, and this is temperature. And then the thinner is the CCSM raw stuff that we're using for the boundary conditions for this WRF run. And you can kind of see that, you know, we're doing a pretty good job here in the summer. We got a little bit of a cool bias at the tails. We got a little bit, and CCSM has got a little bit of warm bias in the summer. Here's precip. The black line, again, is prism. The green line down here, this is CCSM. We found that it's relatively flat. It's even flatter if you look at the Great Plains. But also for the Missouri River, it's got a bimodal distribution, which we know is not true. We got rid of that bias and the bimodality, but we still got too much of a peak here. Again, if we look at the plains, that peak is lower, and if we do our second 36-kilometer run with pulled-in boundary conditions, that actually ends up coming down quite a bit. But we're showing kind of our first bigger run right here. All right, just to give an idea of the spatial changes that we have, this is showing the last 10 years of our climate projections. The average, took the average temperature, average annual temperature, and just a decadal average there, minus the average for 2001 through 2010. You can see a lot of the warming is up in here in Canada in the northern Great Plains. And this is the boundary of the prairie pothole region within the United States. So that's where this model is projecting an awful lot of warmth. If you look at precipitation, you can see that the browns are drying. We got a lot of brown drying along the west coast into this Colorado River watershed area and down in Texas and so on. Not really, just maybe making it up a little bit into the prairie pothole region in the Missouri River area. The gray is not much change, and then the blues is a little bit wetter. So that's, and if you were to look at 2031 to 2040, you would see a whole different pattern. So there's a lot of variability in precip. Okay, so I'm going to hand things over to Parker now.
All righty. Well, the work that I've been doing is working with the WRF simulations that cover the time period 1981 to 2010. And I've been focusing in on the Missouri River watershed also. Initial and boundary conditions that I have are the CCSM3 and CFSR GCM model outputs. And the reference data sets that I use for validation are the CFSR and DAMET. Today I'm only going to show the DAMET reference data set for some of these plots that I'll show later. And I'm going to be showing climate extreme indices, looking at the 6 watershed regions within the Missouri River watershed. Just to remind you, the watershed regions generally successively drain downstream within the Missouri River watershed. It helps us focus in on fairly unique watershed areas within the overall basin. So the climate extreme indices were created by an expert team on climate change detection and indices, and they've created 27 climate extreme indices. These have been used in coupled model intercomparison projects like CMIP-5 and CMIP-3. CCSM-3 is actually part of the CMIP-5 comparison project, CMIP-3 comparison project. And these indices are just used to provide metrics to assess the ability of global and regional climate models to simulate moderate extremes. Think typically of 1 year or less recurrence intervals. Here's 16 temperature climate extreme indices. I'm not going to go through all of these, but they're basically looking at the tails of the distributions for temperature in terms of climate. And then we've got 11 precipitation climate extreme indices. So what I'm going to do first is look at the trends that are common to the entire watershed for 1981 to 2010. And the first 2 indices that I'm going to look at, I will actually have plots for, and I'm going to show plots for Watershed Region 1 and Watershed Region 3. These were chosen because Watershed Region 1 has downward trends in stream flow, while Watershed Region 3 has upward. And even though they're contrasting in the stream flow trends, they have a lot in common in terms of the temperature extremes and the precipitation extremes. So, to start off, we'll look at the annual minimum value of daily maximum temperature. Think winter days in this case. Looking at Watershed Region 1, Damit's in the upper left, and then I've got my 2 simulations to the right and the lower left. And it's in degrees Celsius for the y-axis. What you can see is just that all of them are reflecting a warming in the winter days. Looking at Watershed Region 3, again, you see this warming trend going on, though the simulations do tend to show a greater warming trend than the reference data set does. Then we're looking at the annual minimum value of daily minimum temperature. Think winter nights. Looking again at Watershed Region 1, they're fairly comparable between the reference data set and the 2 simulations, and they're showing a fairly consistent warming in winter nighttime temperatures. And you're seeing a similar behavior in Watershed Region 3. So then these other 3 indices, I'm not going to go into any detail with them, but they're just looking again at how temperature has changed on the tails, and they're all focusing really on the winter months. So what we're seeing is warming in winter months overall. One of the things that I want to note, though, is that these are all temperature trends that are common to the entire watershed. The only place that you see precip trends that are common is in Watershed Regions 1, 2, and 3. So we're going to look at those now. The R10mm, that's the number of days of precip events of at least 10 millimeters. Think fairly heavy precipitation events going on. So we've got an upward trend going on in these 3 watershed regions. If you look at Watershed Region 1, you'll see that Damit's showing a slight increase in these heavier precip days, and the 2 models are showing a greater increase in the precip days than what the reference shows. And then looking at Watershed Region 3, they're fairly comparable, though the simulations tend to show a greater number of days for those heavy precip events. And then next we'll look at the annual total of precipitation. We've got an upward trend in these 3 watershed regions. Again, Watershed Region 1. This is where WRF CCSM tends to show a much greater increase in the amount of annual precipitation than the reference or WRF CFSR. And looking at Watershed Region 3, they're fairly comparable. WRF CCSM tends to be the wettest amount of precipitation, or greatest amount of precipitation, and WRF CFSR sort of splits the differences and is fairly close to the reference data set. And then we've got 2 other precipitation indices relating to precipitation intensity, and then just the amount of precipitation that comes from those heavy precip events. we won't go into any details with those. What's interesting, too, is the temperature range has decreased, and this is really due to the warming of the wintertime temperatures. It's interesting that we see this warming of winter and an increase in precip in these three watershed regions, and yet because of the differences in geology and the shallow aquifer system in watershed region 3, you're getting increasing or upward stream flow trends there, but in watershed region 1, you've got the downward. So in summary, warmer winter temperatures are common to the entire watershed, no common precip trends for the entire watershed, and then watershed regions 1, 2, and 3 show increases in precipitation.
Okay, and so this is John again now, and just in conclusion, I'll just show you some of the products that we have that are coming out. We have actually in press, it's in layout, is a publication on these streamflow trends. Parker's the lead author on that. I am getting ready to hand off 2 layouts all the way through review, and it's had Bureau approval on a paper on the effects of historical and projected climate on hydrologically responsive karst aquifers. And this is the study in Texas and western South Dakota, and it talks a lot about the WRF model in there, the simulations that we did. Parker's got a technical note that is kind of going out to, it just started the review process where we talk about how we linked the GCM, CCSM 3.0 with WRF. I've also got a paper with Susan Scoggin and Parker and Mark looking at streamflow anomalies in the upper Missouri River and climate anomalies, and kind of relating those to teleconnections a little bit. Yeah, so that's been through USGS review. It's got to go out to journal review at this point. Parker's also got his PhD is about 2/3 written, and this last stuff that we're just presenting will be kind of this last third of his work, and there'll be some journal publications on this validation stuff that comes out, maybe USGS pubs as well. And then we'll probably try to get something out on some of those indices for looking at projected climate. We do have some data on the USGS data portal once this SIR comes out in this next month. The WRF 36-kilometer simulations driven by CCSM3, monthly and daily averages of mean surface air temperature and total precip from 2000 to 2050. Those will be available. We want to link that to a pub to make that available. And so that's our presentation. This is the very first picture I took when I moved to South Dakota in 2008. Typical kind of touristy thing to see. And I said, I got to take a picture of that. So anyway, that's it.
Thank you both. I think the easiest way to proceed is if you have a question, go ahead and unmute to ask, and then just please remember to mute when you're done.
So John, this is Dennis. Just a couple of quick clarification questions. In your comparison with the PRISM data, were you also looking at the reanalysis data, or how does those comparisons match up to the basin-wide precip and temperature analysis? And then secondly, when you're presenting the projections out to 2050, what emission scenarios are you pushing the model through?
Oh, yeah, that's a good point. Yeah, that's the A2 emission scenario. Yeah, I should have mentioned that. Yeah, so the A2 it's kind of we chose the A2 in part because everyone else that was doing regional climate model stuff, the NARCAP stuff, was A2, and it's also A2 is the only data that was available at a 6-hour at that time, and we needed 6-hour input to do it. So this is the A2 emission scenario. So the first point is that we're really not using PRISM stuff to look at the reanalysis. We're using the DayMet stuff because it's daily and so on. And I would say that's kind of still on tap. Parker's still kind of working on some of that analysis of comparing the reanalysis that we get versus DayMet. The first cut was looking at it with PRISM, and as you saw that we got it's doing a pretty good job in terms of temperature, and we got that little bit of a bias in terms of precip. So anyways, this is kind of work in progress in terms of some of the validation work. Parker's probably got about another 6 months or so to finish things up on that.
Hey, John, this is Mike Olson. Maybe a quick question for you regarding the James River watershed. How do you tease out the increased flow potentially from the pattern tile drainage that's going on there at a record pace?
Well, I don't know if that is causing increasing flow, and that's a whole nother project. You know, it's a little bit hard to say, and maybe it might affect peaks now and then, but we're really kind of looking at annual flows, and I think when you look at the annual, you know, that water has to go somewhere. You know, if anything, you would think that you would actually get kind of, especially in the summer, you might get decreases because of the fact that the soils are drier now, and they're just not going to run off as fast. But all of that stuff, that tile drainage, I think that's just a whole nother project and direction to kind of consider. But again, once you start to get to the annual level or the monthly level, I think a lot of that stuff starts to even out.
Thanks.
This is Diane Dubinsky from Iowa State. So, yeah, following up on the tile, that was a good question. I was wondering if you folks could talk a little bit more about the Region 6 of the watershed and give us, just a couple comments on the changes there that you saw.
Well, one thing I know about Region 6, that's the downstream, and we got almost all of the flow was down there and a lot of precip, so it's a really wet area. Mm-hmm. I don't know, Parker, if you've got anything that you can say in terms of any of the climate trends and stuff like that. But
I'd have more to say in terms of stream flow. You know, after doing the work on the stream flow, my suspicion is that you've got these upward trends in watershed region 3, and then you've got these. In fact, let's go back to that, just so we've got it up on the screen. Way back. Sorry, I'm trying to get to these annual stream flow trends.
Too many slides.
All right, so you've got these upward trends in watershed region 3, but downward trends in watershed region 5. And my suspicion is that you would have continued to have seen very pervasive upward trends in watershed region 6, except for the downward trends we've got in watershed region 5. You actually kind of see them in the northern part of watershed region 6, and then they sort of more or less peter out. You got a couple more in the lower portion, but you don't really see them once you get downstream of watershed region 5. That's actually our wettest area, and watershed region 6 produces the most volume of water of the watershed regions.
Yeah, and I could just kind of say one other thing in terms of climate is that would be kind of dipping into that area when we looked at there was one plot that showed this kind of spatial pattern of precipitation trends. That's getting into that area where it's projected to be drier out at 2050. And kind of seeing some of those effects, you know, in Texas and Oklahoma these last few years, but we don't have really much in terms of climate trends that we've really identified for that area.
Yeah, it was interesting.
Okay,
so far, the indices that I've looked at for the climate extremes, there's not a lot of strong precipitation changes going on in watershed region 6. It was really clustered in watershed regions 1 through 3. It's the temperature stuff that I'm seeing real common.
Mm-hmm.
This is Bill Travis at University of Colorado. I appreciated the well-organized presentation, and the temperature records are remarkable. When we were looking at yields and planted acreage of wheat in South and North Dakota, one thing we ran into was an increase in winter wheat in North Dakota. And the locals say that it's because there are warmer winters, which you showed in the plot. I'm not really certain what kills winter wheat. It may be just a few cold days, which is one of the measures of duration of cold spells, or average cold plus sometimes with and without snow on the ground. But there's a spread of winter wheat going on that might have something to do with climate.
Right, and here in our backyard, there's the whole issue of the beetle kill and warmer winters as well. Yeah, and we're seeing it actually in the observation, in the PRISM and the DAMET stuff. And PRISM and DAMET are right on top of each other. You compare those two, they're really, really similar. So they're both showing the same thing. And we actually also did a paper where I looked at the actual climate stations, and it validates kind of nicely. So I think those upward trends are real.
Yeah, I've been looking, on the NCDC site, you can plot a set of the averages and monthly for climate division. So I've done South and North Dakota, and you see this too. There's also the slight unusual thing. It's most clear in the area we're actually modeling farmer behavior, which is central North Dakota. The winters are getting warmer, but they keep having these remarkably cold winters every once in a while, but every 10 years, so just this outrageously cold winter comes along, and it does kill the winter wheat.
Yeah.
Maybe this is a Jennifer Francis pattern.
Yeah, you're talking about basically the Rossby wave slowing down?
Yeah, well, and I don't know, but I do notice that if you look at it, go to the NCDC and go to central North Dakota and just do the winter average temperatures, and you'll see this remarkable warming in the records, in the station record, and then these cold winters show up, and they actually the last 50 years they've been getting colder. The cold records, the record cold 3-month average winters have actually been getting colder, and they just had one. I think you guys just had one this year, did you? Yeah.
It was long. It wasn't deep cold, but it was long.
Yeah, and the literature is a little rough on what kills winter wheat. So one more real quick thing: when you read the extension literature and the agronomy notices that come out of North Dakota, they actually explain the growth in the spread of winter wheat as a change in the cultivars being more winter hardy, and almost no one seems to think climate has anything to do with it.
That's interesting. Yeah.
This is Linda Joyce. I had a question with your observation that when you pulled in the boundaries, you got a better comparison with the historical record. And so it's kind of a thinking question, maybe a question for the dissertation exam. Do you think that the boundary conditions and getting those for smaller regions is more important than which climate model you use, that those have a bigger impact than if you had used a different climate model?
Well, just a couple of things there. One is once you pull in the boundaries, your model is more constrained. So it's going to be more and more like the GCM results. So that comes into play. But the other thing is, and this is when we did our WRF simulations based on CCSM, which is kind of what I showed to some extent, where we got that bias. We've been talking with Cindy Briere, who's out at UCAR, and she works with WRF an awful lot. And she says that CCSM has got a cold bias in sea surface temperature. And I think that's preventing some of the convective precip from, basically it's preventing rain when the air mass is over the ocean, and so it comes in a little more saturated. And so it's oversaturated and dumping a bit more. So if we pull in away from the ocean there, we don't get that kind of bias effect of too cold sea surface temperatures. And it could be that it just doesn't show the variability in sea surface temperatures. It's too smooth, so you don't have a trigger to, make it rain out there, that kind of stuff, especially in the summertime. So sea surface temperatures, I think, come into play as well with this stuff. That's part of the story.
Thank you. That's helpful.
The other point you made was that, let me see if I understood, when you pull it in, you also start to exclude those mountains, which were, did the mountains give you the drier or the wetter bias? Did I understand?
The wetter, right. Yeah, we definitely, it does a better job in the plains than in the mountains.
Yep.
Yeah. Yeah, and it would have been nice, actually, if we were able to push that out. There were some limitations in terms of grid size and total grid points in the parallel computing world that we had to make it that size. But I wish we got in the Pacific Northwest a little bit more. Yeah, it's really interesting stuff for us to do as the next step. Look at those two models.
I have us reaching the end of the hour, and so I wanted to thank John and Parker for their presentation, but I wanted to allow a little bit of time for the group here just to update on anything that they would like to share with the group that's online here, and sort of provide some of their research updates or some announcements that you want to share with us. So let's open it up to you all.
Dennis, this is Diane Dubinsky. I have a question about all these presentations. Are they posted on the web somewhere so we can go back and look at these? They're very valuable. So yeah.
Yes, they are, or they will be shortly, and we'll
okay, great.
Send that out to you all in an announcement. I think are they up now?
Yeah, all the ones we've had so far are up already.
Okay.
Under the calendar past events.
So under past events on our website, revamped website, you should be able to find it.
Okay, thanks.
So, Bill Travis, Bill Lonroth, any updates on your research?
Sorry, I was muted. No, nothing to use the group's time right now.
Yeah, I think for me, nothing very newsworthy at the moment.
All right. Anything out of Nebraska? Martha, Mike?
No, I don't have anything in particular to share.
Are things moving along with the sort of the drought work out there? And I guess we had that NIDIS meeting, pilot study. Is that moving along?
Right, yeah. I'm not sure if there are others from Nebraska that can fill in a bit more. So I was actually out on maternity leave when the meeting took place, but it did, there was a pretty large meeting that took place in Nebraska City in late February, and there's a summary report being written about it right now. I think somebody out of South Dakota is writing that, and so that can be, I'm sure, distributed to this group if there's interest for that. So we're just starting at this point to kind of ramp up activities that are related to the NIDIS pilot in the Missouri Basin. At the High Plains Climate Center, we've actually hired a postdoc to do some work, and likely we'll be doing some work with tribes and various community engagement activities. So that's what I know in regard to what's going on with the Missouri Basin NIDIS pilot, but a lot of things are kind of ramping up and going, so I'm sure you'll be hearing a lot more about that in the coming year.
Okay, great. Anyone else have anything to share? And so, I'm just turning over to Geneva for a second. Can you tell us what the next presentation will be and what the date will be for that? The last Tuesday of the month.
Dennis, you just caught me. I did open the calendar on Revamp. The next one, I believe, was listed as Jeff Morissette with an update, and I am trying to navigate into the calendar, but there will be reminders sent out, and it is also it is on our schedule if you can get to it online.
Okay. And do we have one after Jeff's already lined up?
At this point, we do not. And I think part of what we can follow up on after this call is we were going to evaluate how it went after these initial updates or check-ins, and I think it's been really wonderful. So hopefully we continue.
Okay, we could do a little, maybe a survey and see when we want to start back up. We might do this one in June and then take a little break and then pick up in September. Unless there's any other comments, announcements, I want to thank you all, and thanks Geneva for hosting us, and thank you for Jeff in June.
There we go, the 26th.
24th? All right.
Thank you.
Thanks.
Thank you.
Thank you all.